My name is Dan Cziczo, that's how you pronounce this, and I'd like to tell you a little bit about our laboratory and field studies of particles and how they influence cloud formation. And so I was thinking about how to start this presentation, and I wanted to do it sort of graphically with a picture to show you a misconception that we've had for a long time. This is a real image of the Earth, but it's also how we've had a misconception of looking at the Earth system for a number of years until very recently. This was put together by the Japanese Space Agency. It's a real composite image, but they've carefully chosen days that had no clouds and where there was a minimal influence of particles. And so what we know is that this is not a correct representation of the Earth, that at any one time it looks more like this. And so some of the things that we are interested in are, for example, the chemistry of our atmosphere. And we now know that this image is not correct, that for some chemical mechanisms, the classic one being the catalytic destruction of ozone, which takes place on polar stratospheric clouds, you have to consider the particles and the clouds. Another one that we consider is the climate impact. And as you can see from this image versus the last one, the albedo of the planet is really dependent on those clouds that are around the Earth at any one time. Finally, something that's near and dear to the heart of Bostonians is you can't understand the Earth's water cycle, for example, snowfall, until you understand particles, because they're the things that kick off that process. They're the things that nucleate the cloud that lead to that formation. So how does our group tackle this? Well, we have a variety of ways of doing this. The first and foremost is that we have to understand clouds by getting into them. You have to sweep up the material, the ice crystals or the droplets that form clouds, get rid of that condensed phase water to tell what the particles are that are nucleating it. So we use things like research platforms, aircraft, as well as mountaintop sites to get to the clouds we're interested in. We then develop separation techniques to separate those droplets and crystals from the gas phase and the particles that are existing around them. And then we develop tools such as mass spectrometry to understand what the composition is. We also make collections. We take those particles and bring them back to the laboratory to look at them. So we use things like the electron microscope facility at MIT. And this is one example of a particle that was part of a cirrus ice cloud that we were able to collect, bring back to the lab, and look at in depth. And this happens to be a mineral dust particle that's also been influenced by human pollution, by anthropogenic pollution. So you can't simply go make measurements of clouds. It's very important to do that to understand what the particles are that form the clouds. But once you see a cloud, once you go and sample it, it's already happened. It's already occurred. The temperature and the relative humidity that led to that cloud forming has already initiated it, and it's gone away. You've lost that information. So to understand what those temperatures and relative humidities are, we've developed cloud chambers in our labs, ways of mimicking cloud formation, making artificial clouds in lab, but precisely controlling temperature and relative humidity, and then putting the particles in that we know are relevant from the atmosphere. For example, these mineral dust particles that have been influenced by human activities. And the reason that we do this, the reason that we're really interested in this temperature and relative humidity is that this is what's important to predicting, for example, climate, the occurrence of clouds. When are they going to form? Where are they going to form? How thick are they going to be? What's their albedo going to be? And so this isn't a static field. This isn't something that we can just develop these new technologies and just stop there. One of the critical things is that our funding environment, our world is changing. So a few slides ago, I showed you this large research aircraft, the NASA B-57 that we've used for a number of years. Those types of platforms are very expensive and they're going away. We're not going to be able to rely on them for very long. Instead, we're going towards smaller unmanned aerial vehicles. So this is a Global Hawk that's now being flown by NASA. This is the type of platform that we're going to get on. The challenge to us as engineers and scientists is to take the large equipment, the large instruments that we've built for the large research aircraft, and now shrink them down into miniaturized versions of the same thing with the same type of resolution to be able to fit on these new platforms, get to these new remote field sites. So with that, I'd like to say thank you for the time and the chance to finally get to talk to you all, and I'm happy to take any questions. And I didn't get an air horn. Please.
How do you preserve the integrity of a cloud particle, and what does the cloud particle look like?
That's a great question. So for the crowd, how do you preserve the integrity of these particles? That's actually not something that we attempt to do. We attempt to bring in the crystal or the droplet, and we actually intentionally get rid of the condensed phase water, so that we're only left with the little seed on which it formed. There are studies that are interested in that morphology because it's very important to optical properties. And what they do is they impact it onto something like a form var or onto an aerogel, and they try to capture the image and return that. There's also optical instruments, holography, that actually take three-dimensional images of it, although that's not work that we in our group do. Okay, do we have time? One in the back.
How often do you find biological particles?
Oh, that's a timely topic right now. Almost not at all. Biological material is an incredibly hot topic, and one of the reasons that we do field work as well as lab work is that in the laboratory, you can show that biological material is a wonderful thing at creating ice crystals. It's fantastic at it. It's not found in the upper troposphere where ice actually forms, and I think we may hear about this in a future talk, but it doesn't really want to be there, right? Pollens and spores want to stay close to the ground so that they can do what they're meant to do, pollinate and so on. They don't want to be found at 12 kilometers up in the troposphere. They're fantastic at nucleating ice near the ground, not very important to free tropospheric cloud formation.
Thank you, Dan.
Thanks.